All right, here we go. Chapter 6. So we are talking about a continuous probability distribution in Chapter 6 here. So we have two properties of this distribution. We have that the probability distribution will lie, values will lie, between 0 and 1. So 0 is less than or equal to p of x, which is less than or equal to 1. So all of the probabilities are going to be between 0 and 1. And then the sum of probabilities will equal 1. Okay, so we pull that information from last chapter. Normal distribution. So normal distribution is going to be our most commonly used probability distribution. Okay, for a normal distribution, your parameters are mean and standard deviation. And if you recall, with normal distribution, okay, the mean and the median and the mode are going to be assumed to be equal to each other. Okay, so that is this distribution that copied over weird. Let me see if I can pull up the valid one here. Okay, this looks better. So this is our normal distribution. Okay, and if you notice, these all look a little different as the curves, but they are all normal distribution. Notice here the 0 is in the middle of all of these. Okay, and it's looking symmetrical on either side. Okay, so what this chart is telling you is that the larger the standard deviation is, so as the standard deviation gets larger, the more spread out your curve will be. Okay, so very small standard deviation will give you a very thin curve. Okay, standard deviation of 1 is where we are completely normal here. And then as it goes above 1, it's going to flatten out here. Okay, so let's take a look at setting this up. So the probability of x, assuming a single value is always equal to 0 in any normal distribution. Okay, so that's a property. The next property is the probability that a is less than or equal to x, which is less than or equal to b, is exactly the same as the probability of a less than x less than b. Okay, so the probability of x is between a and b in a normal distribution. Again, these are just vocab, okay, for your test. The total area under the curve is going to be 1. It will always be 1. Total area under the curve. Okay, if the mean stays the same, when the standard deviation increases, the height of the curve will flatten. That's what we just looked at with this picture over here. Okay, when standard deviation stays the same, but the mean changes, the shape of the curve actually stays the same here. Because the shape of the curve is determined by the standard deviation. Okay, so in a normal distribution, you are going to have a normal distribution and then a standardized normal distribution. Okay, so in a standardized normal distribution, the mean is going to be 0. The standard deviation is plus or minus 1. The area to the left of the mean is 0.5. And the area to the right of the mean is also 0.5. Okay, the z-score is going to give us the distance between the mean and the data point x on the horizontal axis of the standard normal curve in terms of the standard deviation. All right, so I want to look something up just to show you guys here. Let me see if it will let me copy this. Nope. Copy image. Paste. There it is. Okay. So I'm going to put 2 of these up here, because you need to know the difference between a normal curve and a standardized normal curve. All right, so in a normal curve, let's say you're given this information, the standard the mean of something. We'll say, going back to that M&M's example, okay, the mean, the number of bag of M&M's is 30. Okay, mean is 30. And then the standard deviation is 3. Okay, we'll say 3 bags of M&M's. If I'm setting that up on this curve, I'm going to put the 30 right here. I'm going to put my markings here. So going back to chapter 3 for my standard deviations. So I want one standard deviation that's going to be 33, because I'm adding 3, then 36, then 39, and then going backwards, this would be 27, 24, and 21, because the standard deviation is 3. So when I go from this middle point here over here, this is plus 3. One standard deviation is 3 values. Okay, and same thing here, I do minus 3. Okay, now when I put this on a standardized curve, okay, what I'm doing is I am standardizing my scores. I want to know, let's say, maybe the percentage of M&Ms that are between 32 and 34. Okay, well, to do that, I need to go to my standard curve because I don't have those values on here. So I have to use the z-table, which we'll look at in a second. But all it means to standardize the scores is to use this for your mean. 0, and then 1, 2, and 3, -1, -2, and -3. Okay, where in this case, 0 would mean 30, and 1 would mean 33. Okay, so if I wanted to find a certain value on here, I would use a formula, which we will learn the formula here shortly, okay, to find that value. So standardizing the scores just means making the mean at 0 and then saying 1 standard deviation, 2 standard deviations, 3 standard deviations, instead of actually adding and subtracting those values. Does that make sense? Cool. Okay, so let's go back here. And, well, actually, let's look at our z-table first. Where's our z-table? Here's our z-table. I don't like this one that much. I like this one. They're all the same, basically, but this one is the link that I gave you. I'll give it to you guys again. Okay, so the z-table is z-scores are on a standard curve, so the mean and the standard deviation. So the mean is 0, standard deviation is 1, 2, and 3. Okay, so on a standard curve, the z-score gives you the area to the left. Okay, so if you look at both of these shaded areas here, they both go to the left. So it's telling you the area of all of this under the curve. Okay, and so is this one. This side is negative values because anything to the left of 0 will be -1. Okay, or negative values, -1, 2, 3. This side to the right is going to give you positive z-scores because to the right of 0 are positive numbers. Okay, so it's going to make sense that these are going to have larger areas because it's covering more of the curve, because the z-score will always give you the area to the left. So when we are doing a problem like this, we can look up our z-scores. So what this is telling you is find the probability for our z-score between 0 and 1.95. And those, okay, are your values on the standard normal curve. So it means this. Here's 0. 0 is always right here in the middle. Okay, you want the value between 0 and 1.95. So maybe here's 1 and here's 2. And 1.95 is maybe right here. So you want the area of this shaded region right here. That's what you're being asked to find. Okay, so to find that, you're going to go to your z-score of 1.95 on your chart. Okay, so we're going to go to our chart for our z-table, and we're going to find 1.95. So you're going to go to the chart on the right, and if you're going to go first to your vertical column, and you're going to go to 1.9. So 1.9 is going to be right here. And then this will give you, if you go across it, it gives you the value in the hundredths place. So you're going to look for a 0.05 for where those will meet. And that will be right here, okay, at 0.9744. So you're looking there. So that's 1.95, okay, 0.9744. Okay, so we go back to our chart. This area is 0.9744. But what that tells you, okay, is really that's the area from here, 1.95, all the way over here. Okay, it's the entire area to the left. So it's not 0.9744. But we do, okay, have to take out this part of the curve. We don't want this part of the curve. Okay, so this is half of the curve. So the z-score for 0 is 0.5. Okay, so if we just take this out of 0.9744, then we're going to get the area of this green area right here. So 0.9744 minus 0.5 is going to give us 0.4744. Okay, so that's why I have all of these little graphs here for you guys so that you can visualize them. So in our next example, you have negative 2.17, which we'll say is probably about right here. And then you have 0. So you want this area right here. Okay, so to find this area, you have 0, which is 0.5. Okay, and then you have negative 2.17. So if you go to your chart and you find the area for negative 2.17, then you will get this part. If it will let me, there we go. Nope, there. Okay, so this little part here in the red, and what we want to do is find this part in the black. So we'll have to subtract out this part in the red. Okay, so find negative 2.17 on your chart. So let's see, here's negative 2.1, and then we want 0.07. So that is going to correspond right here to 0.0150. Okay, so now you're going to subtract. And you can subtract this way because probability is never going to be negative, but typically I like to go like this, 0.0150. And that's going to give us 0.485. Okay, and if I look at my curve, that has to look reasonable. 0.485 is almost half of the curve, and if I look at the area shaded in black, that is almost half of the curve. Okay, so here, what is the z-score greater than 2.32? So if you find 2.32, here's 0, 1, 2. 2.32 is probably about right here. So you're looking for this little area to the right. It's not letting me color today. There. All right, so we're looking for that little area there. Let's look up this value on our chart. Okay, so 2.32, 2.3, and then 0.2 right here, 0.9898. Okay, so I have 2.32 is, well, now I forgot it. I just said it. 9898. 2.32, yeah. So 0.9898. Okay, but that doesn't seem right because that's not 90% of the graph. Okay, remember the z-score gives you the area to the left. So 0.9898 is this right here. Okay, it's this whole area. No, that didn't mean to go over it. Okay, this whole area here. So what we want is the area in the opposite direction. So if we just do 1 minus 0.9898, that'll give us this remaining area right here. So 1 minus 0.9898 is going to be 0.0102. Okay, let's do a couple more before I show you how to do this in your calculator. Okay, so negative 1.54. So negative 1.5, maybe like right here. Okay, you're just doing the area to the left. The chart gives you the area to the left, so you just need to find this on the chart. So negative 1.54, negative 1.5 over to 4.0618. Okay, then 1.19 to 2.12. So let's see. 1.19 we'll say is maybe like right here. And then we'll say 2.12 is right here. So you're just looking for the area in between these. Okay, so when you're looking these up, you find each value on the Z chart and then you subtract if you're doing an area in between. Okay, so look up the 2.12 first. 2.12, right there, 0.9830. Okay, then 1.19. Here's 1.1 to 9 is 0.8830. Okay, then subtract. You can subtract like this. It's going to give you a negative number, but then you just turn it positive. Okay, negative 0.1. It's just positive 0.1 because probability cannot be negative. Okay, so then let's take a look with these final two here. You have negative 1.56, which we'll say maybe is about right here. And then 2.31 we'll say is about right here. Okay, so this should be, I'm thinking it's going to be over 0.5 for sure. Going to be a big probability here. All right, so let's look up 2.31. So 2.31, 0.9896. And then negative 1.56 is right here, 0.0594. Okay, so then subtract these values again. And we're going to get 0.9302. Last one we have is just a singular value, negative 0.75, so maybe about right here. You always want to visualize this because we want to know what direction it's going. So find the probability Z is greater than that. Okay, that's going to be to the right. So when we get the probability, it's going to give us the area to the left. So then to find the area to the right, we're going to do 1 minus the area to the left. Okay, so negative 0.75. So negative 0.7. And then 5 is 0.2266. So 1 minus 0.2266 is going to be 0.7734. All right, now you guys are going to kill me because you can do this in your calculator. Okay, and it's really, really simple to do in your calculator. You don't even need the z-table, but I want you to be able to visualize what's happening just in case of any mistakes. So let's take a look at how you do this in your calculator. I do have a calculator handout to give you guys just as a guide, but here's what you're going to do. You're going to go to, where's my pen? Calculator, you're going to go second, and then you're going to go second distribution, so to vars again. Then you're going to go to normal CDF. It's going to be a little bit different for the 83 and the 84. So 83 is going to be, it'll say lower limit, or sorry, 84 will say lower limit and upper limit. You'll put those in. And then pace for the 83, you just do, this will pop up. And then here you're going to put lower limit, comma, upper limit. So this first problem here, you want the z-score between -1 and 1, standard deviation. we should know from the empirical rule that within one standard deviation, that is 65%. Or 68%, sorry. Okay, but we can find this on our calculator. So here's where you're gonna go. Second, okay, distribution, so second bars. Second one here, normal CDF. Okay, then on the 84, it'll say lower limit, you'll put -1, comma, 1. So then upper limit would be 1, enter. Okay, 0.6827. We'll do 4 decimal places for these, 0.6827. Okay, -2 and 2. It's going to look like this. We should know from the empirical rule that's about 95%. And then we can get that in our calculator. Again, second distribution, normal CDF, lower limit's -2, upper limit is +2, 0.9545. Okay, then -3 and +3, that should be 99.7. So it's going to cover most of the curve here. I'm going to look this one actually up in the Z table just to do that. So -3 is going to be over here, 0.0013, +3, 0.9987. Okay, so I get 0.0013 and 0.9987. So that gives us 0.9974. And then let me compare that with the calculator values. Okay, so pretty close. It is close enough so that it will give you the correct value, so 0.9974. So Hannah is saying that on the 84, it's asking for the mean and standard deviation. So the mean, because this is standardized, the mean would be 0 and the standard deviation would be 1 when you're doing this. So if we look at some outside of the normal range, okay, here you have the probability between 0 and 0.567. Hannah, yes, when you have standardized the score, that will always be the case. There will be cases where you can do it without it, but I will always have you guys standardizing the score. So on the calculator handout, I'm going to show you the 2 different examples of when you would standardize and when you don't standardize. And I'm going to do that next class. All right, so this is 0, and then 5, that's not even on the curve, really. That's like way out here. So when I look at this, this is just half of the curve. So this really should be just 0.5. But we can check that mathematically. So we can come over to here, second distribution, and then my lower limit will be 0. My upper limit will be 5.67. And then that will round to 5. Okay, here this is P, the Z value is less than -5.35. So that's like way over here and then to the left. So what would we assume that value should be, or that probability? it's going to be 0. It doesn't really cover much of the curve at all. So that should be 0. Now, let me show you guys this in your calculator here. When there is no lower limit, so if it's just the z-value is less than or greater than something, okay, then you are going to use (99). Okay, so if I'm looking at this, this is actually my upper limit. The z-value is less than 5.35. What I would put in my calculator for this is normal CDF with a lower limit, because it's going to the left to infinity, but we can't put infinity in the calculator. We're just going to use -99. And then it's going to go to the right to -5.35. Okay, so that's when it's going off the curve to the left. We use -99. And that'll give us scientific notation 7 zeros and then a 4, so 0. And then you have, for this example here, there's no upper limit. Okay, so this would be that the z-score is greater than or equal to -7.75. So again, it's coming from way over here, but it's going this way now to infinity and this whole curve. So this should be pretty close to 1 because it's basically the whole curve. Okay, so if we put this in our calculator, we would do normal CDF. Our lower limit would be -7.75. Our upper limit, +99. And then we get 1. And then just one more here. The probability that the z is greater than 10. What do we think this is going to be? 0. Yeah, that's going to be 0. Okay, here, our upper limit, so this would be normal CDF. We're going to the right. Okay, greater than 10. So 10 would be our lower limit. 99 would be our upper limit. Oh, I put 0, sorry. Okay, so 23 zeros and then a 7. So safe to say that's 0. All right, and that is all of 6.1. So let's take a look at 6.2. Now 6.2 is going to go back to kind of what I did here in standardizing the score, but now looking for certain values within our standardized scores. So when we're standardizing the score, you're going to have this formula here, which is the z-score, okay, in a standardized curve will be x, so the x value minus the mean over the standard deviation. So where do I put a score on my curve? I'm going to do this formula, and then it'll tell me where to put it. So for example, okay, assume all IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. So if I drew a bell curve for this, I'd have 100 in the middle, and then I would have my 1, 2, and 3 standard deviations on either side. Okay, for my right side, I would add 15 each time. So 115, 130, 145. And then on the left side, I would subtract 15. So 85, 70, 55. Find the probability that a randomly selected person has an IQ between 85 and 100. All right, so when we take a look at this, what we want to do is we want to standardize each of these scores. Okay, so let's see here. You are going to find, okay, the z value for 85. So you're going to go like this. I'll do it up here. X is 85 minus the mean is 100 over the standard deviation, which we were told was 15. Okay, so 85 minus 100 is negative 15 over 15 is negative 1. So the z-score for 85 is negative 1, which we can see on this curve. It is exactly 1 standard deviation. So it's negative 1. So this negative 1 corresponds in the context of this question to an IQ score of 85. Okay, then we want the 100. Well, that 100 is just 0 because 100 is our mean, but we can do the formula. 100 minus 100 over 15 would give us 0. So we want the probability between negative 1 and 0. So we want this value right here. So we've standardized our scores. Now we can either look them up in our z-chart or we can put them in our calculator. I'll put in my calculator, normal CDF, negative 1, 0. So the probability in terms of the z-scores, negative 1 and 0. And that's going to give us 0.3413. So what this is saying in the context of this problem is that there's a 34% chance that if I select a random person, their IQ is between 85 and 100. Okay, in order to get that number, I have standardized the score. So you have to make a few assumptions about this. And what happens here is it says assume that it's normally distributed. Okay, so if it says it's normally distributed in the problem, which the rest of our problems for chapter 6 and 7 will be, okay, that means that the average is equal, or the mean is equal to the median. So 100 is the mean and the median of all IQ scores. So we can do this using the empirical rule, or what do we have here? We're just going to standardize these scores. So if we take a look at here, find the probability that a z, these should say z, I'm sorry, they don't say it, but find the probability of a z being less than 85. Okay, so what we would want to do here is convert this to a z-score. So z equals 85 minus 100 over 15. We already did this one, so it was negative 1. But now we're looking at this probability here. So if I have my little chart, and sometimes you can just draw a quick one here. It's not very good, but works. Negative 1 is right here. This is what I want. I want this probability. I do this just to visualize it, just so I know, all right, it's not going to be more than half of the curve. So if I get a number that's more than half, I'm going to want to take that one off or check it again. So here I would have a lower limit of, what would my lower limit be here? If I'm going to the left, I'm going negative 99. Yep. And then negative 1. Okay, so that is 0.1587. So 0.1587 here. Okay, then 70 and 130. Okay, so let's find the z-score for 70. So 70 minus 100 over 15. That's going to give us -2. And then 130. 130 minus 100 would be 30 over 15. That's going to give us +2. So there I'm going to want normal CDF with a lower limit of -2 and an upper limit of +2. Okay, so that's 0.9545. And then let's look at the 115. So find the z-score. So 115 minus 100 over 15, that should give us 1. And you're looking for it to be greater than that. So what you're looking for is this. Here's 1 to the right. So then we would do normal CDF with a lower limit of 1 and an upper limit of +99. And that will give us 0.1587 again. Okay, so this one's going to the right of 1, this one was going to the left of 1, but it's the same probability, okay, because it's still the same area on the chart, just going in different directions. Okay, and then we can look at some probabilities that might not necessarily lie right on our chart, so they're going to be in between these numbers. So that's where we go looking at these. So find the probability that the z or the x is less than 105. Okay, so what we want to do is we want to standardize that score by using the formula, the z equals x minus the mean over the standard deviation. So here we would go z equals 105 minus our mean of 100 over my standard deviation of 15. So that should give me 0.3333. Okay, then what it's asking is the probability that x is less than that value. So if I visualize this on my curve, here's what it's asking. Here's the score, 0.3333, which is maybe about right here. Probability that it's less, which would be going to the left. When it's going to the left, we have a lower limit of -99. So here I would go normal CDF, -99, comma, 0.3333. So I get 0.6305. Okay, then we're going to do the same thing for number 2. Okay, you want the probability that the IQ is between 72 and 95 for a randomly selected person. So we want to standardize each of these scores. So find the z-score for 72. So 72 minus 100 over 15. So that's going to give us -1.8667. And then the z-score for 95. 95 minus 100 over 15. And that'll give us negative 0.3333. Okay, then visualize what you're being asked, the area between these two numbers. So here's 0, and then negative 1.86 is maybe right here. And then negative 3.33 is still to the left of 0 right here. So we want in between these two numbers here. So we're going to go normal CDF, negative 1.8667, negative 0.3333. And we're going to get 0.3385. Okay, and then number 3, find the probability the IQ is over 120. Okay, so standardize the score. So Z will equal 120 minus 100 over 15. So 120 minus 100 over 15, 1.3 repeating. Okay, and then we're visualizing that as this. Here's a 1.3, and we want it greater than that, so to the right, which means our upper limit is positive 99. So this would be a normal CDF. Let me see if I can write it right here. Okay, 1.3 repeating, positive 99. And that's going to give you 0.0912. All right, before we move on to our questions, does anybody have any questions? Okay, so let's take a look at these exercises. So in the first one, we have a study of elite distance runners. The mean weight is reported to be 63.1 kilograms with a standard deviation of 4.8. Assume the distribution is normal. Sketch the density curve of the weight distribution with the horizontal axis marked in kilograms. So this means just draw the curve. All right, so 63.1 is your mean. And you're going to have 1, 2, 3 standard deviations to the right, 1, 2, 3 standard deviations to the left. So 1 standard deviation to the right, you will add, let's see, 4.8 each time, which will give you 63.1 plus 4.8, 67.9, then 72.7, then 77.5. Then here we'll subtract 4.8 on the left each time. So that's going to give us 58.3, 53.5, and 48.7. And that's it. Anybody know what 63.1 kilograms is in pounds? .2 is our multiplier, so 138.82. Okay, number 2, Jill scores 680 on the math part of the SAT. Distribution of SAT scores in reference population is normally distributed with a mean of 500 and a standard deviation of 100. Jack takes the ACT math and scores a 27. Okay, ACT scores, same thing, with a mean of 18, standard deviation of 6. Who has the higher score? Why? So you can put both of these, okay, find the z-scores for both of them, and then put them on the same curve because you are normalizing or standardizing the curve for both of them. So for Jill, okay, you have an x value of 680 minus a mean of 500 over a standard deviation of 100. So that will give us a z-score of 1.8. Okay, so if I'm drawing this curve here, and this is your test scores curve, here's 0, 1, 2. Jill is about right here. Okay, then let's do Jack. Okay, Jack has a 27. The mean is 18. Standard deviation is 6. So 27 minus 18 over 6 will give us 1.5. Which means Jack is about right here. So who has the higher score? Jill has the higher score because her z-score is larger. She scored more, okay? She had a higher score than this whole percentage of the population. Jack had a higher score than this whole percentage of the population. Okay, Jill scored higher than a greater percentage. And if you wanted to find those, what is that going to be? Jill is 96.4. I think Jill scores higher than 96.4% of the population. And Jack scores higher than 93.3%. Okay, so because Jill's was a higher percentage of the population, hers is higher. And I found that just by going, okay, so normal CDF. For Jill, it would be 1.8 and then 99. Oh, it would be negative 99, sorry. Negative 99 and then 1.8. So that gives you that 90.964. And then for Jack, same thing, negative 99 and then 1.5. 93.3. Okay, we just converted it to percents because we're dealing with a real world problem. All right, and then we have this one here. We've got quite a bit to do with this one. Okay, in recent years, there's been considerable discussion about the appropriateness of body shapes and proportions of Ken and Barbie dolls. They may be viewed as controversial, ideal body shape, okay, potentially leading anorexia risk. All right, so they scaled them up to a common height of 5'7", compared them to body measurements of active adults. Common measures of body shape are chest, waist, and hip. And here's your reference groups. Okay, so what this is telling you here, this is the doll value, the human mean, and the human standard deviation for each of these. Okay, so what it says here is convert Barbie's chest, waist, and hip measurements to z-scores. So Barbie, okay, your chest measurement, you're just converting this to a z-score. So this is your x, this is your mean, this is your standard deviation. Okay, so for chest, we would do 82.3 minus 90.3 over 5.5. So that gives us a negative 1.4545. Okay, then her waist. So that's going to be 40.7 minus 69.8 over 4.7. So negative 6.1915. And then hips would be a 72.7 minus 97.9 over 5.4. And that's going to give us a negative 4.6667. Okay, so that's your first one. Second one is Ken. Okay, so you're going to do the same thing with Ken. You can see up here. So Ken, we would go chest first. So that would give us a 75 minus 91.2 over 4.8. So I'm going from Ken's up here. So that's going to give us negative 3.375. His waist, we're going to have 56.5 minus 80.9 over 9.8. And that would give us negative 2.4898. And then his hips, you would have 72.0 minus 93.7 over 6.8. So that would give us a negative 3.1912. Okay, and then part 3C, do these z-scores provide evidence to justify the claim that Barbie doll is too thin of a representation of adult women? Justify your response with an appropriate statistical argument. Did anybody want to share their response to this part of the question? Okay, well, I might write something like this. I would say, yes, these z-scores do provide enough evidence to justify the claim that Barbie is too thin of a representation because all of the values are less than the mean, okay, are less than the mean measurements for adult American women. So I'd say that. And then to prove it with a statistical argument, I would find the percentages for each of these. So I would go for the chest, normal CDF, negative 99, and then negative 1.4545. So that is going to represent about 7% of women, okay, which means 93% of women are misrepresented there. Okay, hips, going to be even worse. So negative 99, negative 4.6667. Okay, that is less than 1%, 0.000001. Okay, less than 1% of the population is represented with that hip size. And same thing with this one, that's going to be 0 again, negative 9, and then for the waist, negative 6.1915. Okay, same thing, so less than 1% of the population. So in order for Barbie to be more statistically accurate to the adult sizes of, or the mean adult size of American women, we would want to make sure her measurements were within a 50% range. Okay, so something like that. And then same thing with Ken. If you look at these, you can kind of tell those are all going to be about 0, close to 0 as well. Does anybody have any questions? Okay, well, if you don't have any questions, you are free to go. And if you do, you can stick around for a few minutes. You guys have a great weekend.